did in the last class. Are any other doubts, questions you have? So you can ask, then I'll start. So are there any questions? Yeah. So you okay? So that's one. I think there is one more question. So although I wanted to start FEM today, but then let me start with first the question which I had given in the last class. So see, that was no derivation of integral functional. So I had said that now if you have this differential equation d by d2 by dx square of ei d2v by dx square minus q is equal to 0. So this is the differential equation actually governing the deflection of a beam under no Euler-Bernoulli assumptions. So first we write the weighted residual statement. So WRS is integration over the length of the beam W, and then this no differential equation as it is d2 by dx square of ei into d2v by dx square minus q dx is equal to 0. So this is the weighted residual statement. Then you write the weak form. So you have to do in this case, as you see, there is a fourth order derivative of the dependent variable v and w. So we can actually do the integration by parts twice to transfer the derivatives equally between the dependent variable v and weight function w. So if you do that, you do the integration by parts twice for the first term. So first what you will get is actually w into d by dx of ei d2v by dx square. This is the one boundary term you will get, 0 to L. Then another boundary term would be dw by dx into ei into d2v by dx square, second boundary term. I am directly writing the final form whatever you will get. And then the this is then finally you will have plus here integral 0 to L d2w by dx square into ei into d2v by dx square dx, and of course the last term is minus integral 0 to L w q dx is equal to 0. So this you will get as your weak form. This is actually doing, I have written directly. No, you first do the integration by parts once for the first term, and then in that you will have one boundary term, one integral term. For the integral term again do the integration by parts once again. So this is what finally we'll get. And then here we take w to be basically variation in v, which is your dependent variable. So let w be equal to delta of v. So once you do that, and then for the timing, let me, although later I am also going to take these terms non-zero when I will develop finite limit, but for the timing let me say the boundary conditions are such that either this term is 0 or this term is 0. So let us say that for a given problem and boundary condition, the boundary terms are actually 0. So for example, if I take a cantilever beam and subjected to distributed force, and this is your x and this is y direction, v is actually in that direction, v is the function of x. So here see v and dv by dx are 0. So that is at x equal to 0 lower boundary, w and dw by dx would be 0. So these boundary terms would be 0. our upper boundary, the shear force as well as bending moment is 0. So since the second term is 0 in both the boundaries, both the boundary terms at x is equal to L, so boundary terms are going to be, in this case they are going to be 0. So for this particular case, then finally what we get, this weak form, taking these boundary terms to be 0, that is this is 0, this is 0 for the given problem. So what you are left with, and taking w equal to delta v, integral 0 to L d2 dx square of delta v ei d2 v by dx square dx, that's the one integral term, minus integral 0 to L delta v q dx. This is the second term, this whole thing is equal to 0. Now what we do, we basically take out variational operator delta common in the whole of this expression. So first what you do, of course, here that this delta and the differentiation, they are interchangeable. So I know you can write that as delta of d2 v by dx square, and then when you take out delta from the first, so what you will get is, let me write that, so integral 0 to 1, and then this is like, you have delta of, so again the same concept, that when you write say x dx, this is 1 by 2 essentially d by dx of, or d of x square. So x dx's are, when you do this d of x square, which is x2 into x into dx, so you get the same thing divided by 2. Same here you do, this is like delta of d2 v by dx square into ei into d2 v by dx square. So that can be written as delta of ei by 2 into d2 v by dx square whole square dx. So that's the first term when you take out delta common, because right now what is written is, after interchanging these two, the first term is delta of d2 v by dx square into ei into d2 v by dx square. So that I am writing as delta whole delta ei d2 v by dx square whole square by 2. So that's the first term. That is when I take delta common out from the first term, this is what I would get. And the second term is straightforward, so that is minus integral 0 to L, and delta you are taking out, this is anywhere known quantity, so variation is only with respect to v, so it simply becomes vq dx is equal to 0. And so this we can say something like delta of integral functional I equal to 0, where I is integration 0 to L ei by 2 d2 v by dx square whole square dx minus integration 0 to L v q dx. So this is your integral functional. This is actually total potential energy. You can see that this would be strain energy stored in the beam, and this is the potential of distributed force, taking datum as the undeformed configuration of the beam. So this is what you were actually expected to do in that. So anyway, we will be using some of these subsequently as well, but you must know, so if there are similar kind of problems, you should be able to, suppose you take a heat conduction equation in 1D, you should be able to derive such functional, if your two-dimensional heat conduction equation, should be able to derive the integral functional for that. So then let me start with finite element today. So far whatever we have actually done is just the basics which are required for this. So I am going to as the name suggests, finite element. So you have an entire domain, and finding out an approximate solution which is valid over the entire domain is actually again usually a difficult task, or you get simpler solutions which are highly inaccurate. So you try dividing the domain into smaller subdomains, and then you are looking for piecewise continuous solution. This is piecewise continuous approximation, let me say. So this is what actually you are doing. Rather than assuming an approximate solution which is valid over the entire domain, you are doing the discretizing the domain into smaller pieces, and within each piece in finite element you are assuming an approximate solution, and of course you will have to find out the constants in the approximate solution, so you set up the equations for that. So this is essentially what finite element is, piecewise continuous approximation of field variables. are your dependent variables. So piecewise continuous approximation of field variables like displacements and so on, field variables, essentially nothing but they are dependent variables. So if you look at usually the steps, so first step is obviously you have to discretize the domain into smaller subdomains. So the first step is discretization of domain, that is entire domain, into smaller subdomains, and these subdomains are what we call as elements, finite elements to be more precise, and these finite elements are connected by nodes. So the elements here, elements are connected through points which we actually call nodes. So that's the first thing, and once you do this, then the next is we have to develop the equations governing unknown constants in the approximate solution within the element. So we call this step as develop element level governing equations. These are actually algebraic equations. That's the second step. So we convert essentially either we have differential equation corresponding weak form or integral functional. We finally convert all of that into set of simultaneous equations. And because this at this step what you are doing is developing governing equations which are referred to as element level governing equations for one element, and of course these are usually general enough that no similar form is applicable to other elements. Then you have to join all of them together. So this joining process of element level governing equation for different elements is referred to as assembly. So when we actually do, we will be clear more about this. So this is assembly of all elements, and after the assembly, of course there are techniques where during the assembly also you can impose the boundary conditions, or they can be techniques where you are imposing the boundary conditions later, but they have to be done. So next step is imposition of boundary conditions. So that is now as far as the boundary conditions are concerned, you are doing at this stage. So we will see how we actually do this, whereas when we were trying to talk about approximate solution for the entire domain, we said no essential boundary condition in case of big forms should be satisfied a priori before we set up the equations further. So imposition of the boundary conditions, then solution of simultaneous equations, whatever we get. These equations are set of simultaneous algebraic equations, and the next step is post-processing. Post-processing, what you are doing, because here you get the solution of basically what we call as degrees of freedom. So post-processing essentially is you calculate the derivatives of field variables. For example, strain in solid mechanics, you calculate stress, reactions, and any other quantity you want to calculate within each subdomain, that is element. That all you actually do under post-processing. So if you are using a package, so typically the first step is referred to as pre-processing. So wherein also you will, of course, precursor to this step would be first solid modeling, that is you have to make a solid model. That solid model could be just lines, curves, or it can be surfaces, or it can be solids. So this actually usually referred to as, so step 1 is usually referred to as step 1 is referred to as pre-processing, and some softwares like ANSYS, even though there is a menu which is as it is named pre-processing, other packages the names might be different, but essentially it does the same thing. And if you look at steps this 2, 3, 4 and 5, so steps 2, 3, 4 and 5, these are referred to as actually the solution step, wherein you are setting up the governing equations, then in assembly, imposition of boundary conditions, solution of simultaneous equation, all of that comes under solution. And the last step is obviously the step 6, which is already I have written as basically post processing. So if you are using packages, then what you are doing, you are spending your most of the time doing this. Of course, if you are using a package, means you are solving fairly a complex problem. A simple problem can of course always be solved. So most of the time you spend in your pre-processing, creating solid model discretization, choosing right type of element for the discretization, or maybe combination of elements, different types of elements, and then discretization, giving the loads, boundary conditions. Then you just submit it for solution. So internally, the software will have different subroutines. It would, the main program would call all those subroutines sequentially. First element level governing equation for each element, assembly, then next element, and so on, imposition of the boundary condition, solution of simultaneous equation. All of that is done. Actually, the software, which is if you are using a software, it's just like a black box. So you don't know what is going on inside. But these are the the major steps are actually in that 2, 3, 4, and 5 which are going on. And then of course the last step is post processing. So software already if you request a priori that these are the quantities you would like to look at later, so it also calculates those, and then just view, you can look at the numerical values, graphs, contour plots, and so on. So that is what you do. So most of the time you look at this and look at this. But to do these steps properly, you actually need to understand these, and that is why the course like this is important, even if we are actually going to use commercial packages. Of course, those who develop their own finite element codes for solving new type of problems and things like that, they have to obviously do all of this anyway. So this is basically the basic steps involved. And typically, if you look at the classification of finite elements, so we classify them into type of elements. Usually, we call them as 1D, 2D, and 3D. So when you say 1D, what it means is, all the time whatever domain you are dealing with, usually physical domains are always actually volume, so they occupy a space, some volume in space. But here what then we are able to some kind of able to make some approximation such that our field variables are the dependent variables are functions of only one coordinate. So here what you are saying that dependent variables are functions of one coordinate. So it maybe you choose either a Cartesian coordinate, so x coordinate, or curvilinear coordinate, maybe theta coordinate, r coordinate, whatever it is, depending on the problem. So dependent variables are functions of one coordinate only. Here when you say basically unknown functions, right? There can be known functions, one coordinate. In case of 2D problems, the dependent variables are unknown functions of two coordinates. So unknown, that is dependent variables are unknown functions of two coordinates. Make say xy, or even can be curvilinear coordinates. And here then basically they are functions. Obviously you can make out all the dependent variables are functions of all the three coordinates. And this, whether for a given problem you are going to use this, are you going to use this, are you going to use this, depends on the physics of the problems. You must understand the underlying assumptions, what are the possible ways of reducing a problem from a 3D to 2D or from 2D to 1D. So we need to know the essentially for the given problem we need to go for 3D or 2D or 1D. In solid mechanics, so this is we will, when we develop the various types of element, we will understand more. So in case of solid mechanics, if you look at we have further classification. And so in 1D what we would be doing, and we would also be actually discussing this. So one dimensional elements, you have essentially what I am going to do, truss and beam And in beam again, two types of elements, Euler-Bernoulli, Timošenko beam, and of course there are higher order elements, but we may not do that. And in truss we'll also look at modeling of 2D and 3D trusses. So this is what we would do in the 1D elements. Then in 2D you have what are known as plane stress, plane strain elements, axisymmetric, and then you have plate bending elements. So these are usually in solid mechanics you have two-dimensional elements. So we look at what are the approximations made in this, and then of course 3D they are essentially volume elements, and you have there are no approximations as far as the variation of field variables is concerned within the domain. Still there would be other approximation about the material behavior and range of strains, boundaries and so on, but as far as the here there are no, so usually we call these as brick elements. This also can be degenerated to a tetrahedral elements. Of course the shape I am not talking about, I will talk about when we look at these things in detail. So I would be covering in this course most of these, in addition to of course some examples on maybe heat transfer and also fluid mechanics problems, some maybe electrostatic problems, so that you have the idea about it's not just limited to solid mechanics, but the same approach is applicable for other problems as well. So now the important thing, as I said, is actually this step. So most of the time we would be actually spending in developing the element level governing equations. Initially we'll take problems where we do the first, second, third, all the steps, but later we would spend most of the time in developing the element level governing equations. So that is what I am going to start today, development of element level governing equation. So now see, this is essentially we will initially work with integral functional, that is total potential energy functional, but the same equations can also be derived from weak forms. So the again steps involved here are that you have a problem and you have say governing differential equation, then you can derive the weak form integral functional, so you have all of that. And then again here if you look at steps, usually the first step is, of course you have, as I said, weak form or the integral functional. Then first step here is to assume an approximate solution. Assume an approximate solution for the dependent variable. Assume an approximate solution. This is valid within the element, that is within a subdomain. So as first step is assume an approximate solution. Now when you do this, what are the requirements? So we actually talked about the requirements of approximate solution in the approximate analytical solutions itself. So most of those are actually applicable here. So the first thing is differentiability requirement. So this is as per weak form or integral functional. If you are actually using strong form without weak form, then the differentiability requirement would be as per that. So ultimately forever this approximate solution is going to be substituted, and whatever is the highest order derivative present in that equation, your approximate solution at least should be differentiable up to that order. Then the second requirement for the approximate solution is that it should be a complete set of functions. So most of the time, since we use polynomials, so let me say that this should be a complete polynomial. When you say complete, meaning is, suppose you need highest order derivative as second derivative, so at least you have to have x square term. So then you should have a constant term x square. Of course you can go on the higher side further. So in 1D essentially, again if you look at for 1D problems, the sequence is obviously we are using polynomials, so it has to have, depending on what is the highest order term, x square, x cube, x power 4 and so on. So if you want to include x square, these must be there, this should be there, this should be there. If you want, your problem requires the inclusion up to x cube, so you must have 1x square. And these also, the inclusion of these terms also actually represent, maybe sometimes you have a rigid body motion or a constant gradient, the constant field variable within a domain. So unless and until you have, let's say, this constant term, your approximate solution cannot represent the constant value of field variables within the given subdomain. Sometimes it can be even over the entire domain. Sometimes gradient may be constant. So unless and until you have this term in the approximate solution, it cannot represent that. So essentially, the idea is that we should be able to capture all the basic possible solution scenarios for given problems. So that's the one thing. When you are looking at 2D problems, so 2D means, let's say, in Cartesian system, you can also work in other coordinate systems. So there is something called Pascal's triangle. So you should have a constant term, then you should have a linear term in x and y, then you should have quadratic terms x square, xy, y square, and so on. I'll actually again discuss in more detail about this. So if suppose you want to include only 4 terms in the approximate solution, then what you would do is constant, linear in x, linear in y, and then you would actually go with this term. Okay, so there are no further steps involved, but for the timing, I just wanted to tell you what is the meaning of complete polynomial. If you are using polynomials as your base functions for assuming no approximate solution. Then the third requirement is actually inter-element compatibility. That means what variables should be continuous across the elements. So inter-element compatibility requirement. And what you need actually, that your primary variables must be, or in solid mechanics, geometric quantities must be actually continuous across the elements. So here, for general case, we would say primary variables should be continuous across elements. So this actually decides the boundary nodes what should be the degrees of freedom. So these are the basically guidelines which need to be satisfied when we assume approximate solution. Now in finite, see in the, so is this all the 3 requirements clear? Differentiability, so look at your weak form or integral functional, what is the highest order derivative? You have to assume an approximate solution which is differentiable up to that order. Then you have to, in that process, you will have to make sure that you have, if you are using polynomial, it must be a complete polynomial. Then next is that you have to also make sure that you have the terms which can represent the primary variables as degrees of freedom at the boundary nodes of the elements, and therefore you can ensure this continuity requirement of primary variables across the elements. So that is known as inter-element compatibility. And depending on what is the kind of, if you require only field variables to be continuous across the elements, we refer to them as C0 elements. So again, within this there is a classification we call as C superscript 0 is represents actually continuity. So C0 elements. So C0 meaning is that only field variables are continuous across the elements. So C0 means no derivatives are continuous. C0 simply the variables. So here field variables, FV I am using for field variables. So field variables are continuous across elements. Then you have what is known as C1 elements. So C1 element means a field variable and their first derivatives are continuous. So that is what this one means. First derivatives also field variable and their first derivatives are continuous when we go from one element to another element. That is when we look at their distribution across the domain, we are passing through each subdomain or elements. So field variables and their first derivatives. So field variables and their first derivatives are continuous. and then you can know similarly you can have C2, C3 and so on depending on the problem. Most of the time we actually confine with C0 and C1. There are a lot of problems in developing these kind of elements, but no, it's very simple to develop C0 elements. Most of the time we actually use those, these C0 elements. So once we assume an approximate solution, so now the second step is earlier what we were doing in the approximate analytical solutions is that we said eliminate some of the constants by satisfying your essential boundary conditions if you are using weak form. Now here, because this element might lie somewhere within the domain, so it's actually not in the boundary. In general, it is not going to be in the on the boundaries of the domain. So what we do here, express the unknown constants, and the reason for that is so that we can directly ensure this C0, C1 or C2 continuity depending on the problem. So express unknown constants in the approximate solution in terms of your elemental degrees of freedom. So I will talk about what are those elemental degrees of freedom. So this, as I said, in nodes must have primary variables as degrees of freedom, and an element might have multiple nodes, so boundary nodes, and also it can have interior nodes. In interior nodes, you can have degrees of freedom lesser than what you have at the boundary nodes. So when you count all of those variables across all the nodes of an element, that all total together is referred to as elemental degrees of freedom. So we in the next step express unknown constants in the approximate solution in terms of elemental degrees of freedom. We have, as I already said, the boundary nodes must have primary variables as degrees of freedom. So that's the first guideline which comes. And if just let's say 1D you have two boundary nodes, and each boundary node there is only one primary variable, then elemental degrees of freedom would become 2. If you have, let's say, primary variables 2, maybe the variable and its first derivative, and two nodes in an element, then the elemental degrees of freedom would become 4. Nodal degree of freedom would be 2. That is, two primary variables at each node. So this is the second step, and the third step is, these are just the steps. We are actually going to do a lot of things. So using this, so you'll understand more and more. Of course, it's obvious that what I'm talking about here. Then the third step is, then you'll have to basically convert the this integral functional of big form into set of simultaneous equations. So substitute the approximate solution in the integral functional, substitute the approximate solution, whatever you get in step 2, in either weak form or integral functional, and obtain element level governing equations. So these are the actually steps as far as the development of element level governing equations is concerned. I am going to start with an example. So are the broader steps clear? I think I wrote too many things. So if there are any, let's take a pause for 2 minutes. So if there are any doubts, questions you can ask. Yeah. Yeah. So this is like if you have, let's say, the fourth order differential equation. So then variable and its first derivative would be primary variables. So what I was talking about is, for when I was talking about this express unknown constants in the approximate solution in terms of elemental degree of freedom. So what I am saying is that, say this is your element and this is represented by only, and how we decide this also we will talk about. So these are the two nodes, and in a given problem, let's say we want primary variables are v and its first derivative dv by dx, because this element would get connected with the other elements. So unless and until we have these variables which are primary variables as degrees of freedom at the end nodes, we cannot ensure their continuity. So we need to have these as the nodal degrees of freedom. So here nodal degrees of freedom 2, since there are 2 nodes, so you have also this other side node also these 2 degrees of freedom v and dv by dx. Maybe you may call this as v1, this as dv by dx at 1, this is v2 and dv by dx at 2. So here in this case, when we have 2 primary variables and 2 nodes in a 1D element, so we have 2 nodal degrees of freedom, that is this and this, and the second node also 2 nodal degrees of freedom. When we look at whole element, there are 4 degrees of freedom. Why we call these degrees of freedom? Because once we know these, we can actually look at what is the deformed configuration of the element. So essentially these variables are needed finally to know the deformed configuration of the element, and that is why the term degree of freedom for the element, that is elemental degrees of freedom. So this is what I was talking about, that in this case the elemental degree of freedom would be 4. If you have only one primary variable, the variable itself, dependent variable, and only 2 nodes, so then you have elemental degree of freedom only 2. Okay, so this is what I was. Is there any other question about any of these steps? Decide the essentially, so from the order of differential equation, you know the primary variables, and once you know the primary variables, you know that what should be the degree of freedom at boundary nodes, and then whether to have only 2 nodes or whether we can go for more nodes, that we would look at further. So this is, are there any other questions? You should also ask no questions, doubts, even if whatever could be the doubt, no, even I would have clarified, talked about it, but still you should ask if you have a doubt. Okay, so are there any questions? No. Yes. So let me then take as an example. So I am going to start today with what the simplest example we talk about is 1D truss element. So that is the element I am going to start with. So this is governing a problem like you have a rod and the length is significantly greater compared to the cross-sectional diameter, and there are forces which are acting only along the significant dimension, that is length. Let us say this is a distributed force Q. Boundary conditions could be anything. I am just sketching one representative boundary condition, that one inlet is fixed, this is x, and after the application of the force each point is going to move. So let's say that displacement is u, which is a function of x. So this is the problem, and for this we want to develop essentially the element level governing equations, and then we'll also look at the other steps. So when we develop the element level governing equation, of course actually this problem here, since this variable u, which is the displacement of the rod along its length, is assumed to be function of only x coordinate, and that is why this problem is a one-dimensional problem, because your dependent variable is function of only one independent coordinate, that is x in this case. So essentially your domain is here just a line. When you talk of domain, it's just a line as far as the representation of the domain for the finite element formulation is concerned. So then what we do, we discretize this into a number of elements. Like you divide into a smaller pieces, and how many pieces, that we would talk about in terms of convergence study, but for the timing let us say we have this discretization. Then we want to develop these are different elements 1, 2, 3, you can give some numbers. We want to develop the element level governing equation for some element, let us say this. So what we do, because this is connected with the other elements, so first would be that draw the free body diagram of the element. So let me still draw the FBD of this element here. So one is that it has distributed force within this, okay, and because it is connected to this element this side, so there would be force here. It is connected to this element this side, so there would be force here. And here the force means actually axial force. So as per as I was talking about the sign convention for the stress, so similar way here you take the axial force, the line I want to draw at the center. So the axial force is, let me say that this notation I am going to use, this is Q1, and let us say this is Q2, and this is element number, let us say E, so I'll also put the superscript E here, and this is your distributed force Q which was already acting there. So this is a free body diagram of the element. Essentially you are separating this out and drawing all the forces acting on this. So when you have this side, it would be stretched by this element, so that force is this side it is going to be stretched by this element, so this is the force. I am assuming that these forces are positive, so they are positive along outward normal to a given section. So this section outward normal is along positive x, so this force is shown along positive direction. This section outward normal is actually in this direction, so positive force is shown in this direction. So this is just the free body diagram. We have BD of element, free body diagram. Then we need to write, let's say, the integral functional for this. This problem is governed by, so the governing differential equation for this problem is still that second order differential equation, and we had already derived the weak form of this, and in that weak form only thing what I am going to do is, if you recall, I had written this I for the second order differential equation. So the I was half of integration. Now this, since we are doing it for the element, and so we will be doing the integration over the element only, not over the entire domain. And let me also do one more thing, that let me also introduce a local coordinate system. So x is the global coordinate which is having origin here, x equal to 0 here and x is equal to L here. Now let me take say a local coordinate system, say capital X here. So the capital X means it is capital X is 0 here and capital X is equal to small l, where small l is the length of this element. You can actually put the superscript E for this particular element, but just to minimize every time I have to put superscript, I am just taking it as L. So this capital X is a local coordinate with origin at the left end of the element. So X is local coordinate with origin at the left end of the element. And actually this coordinate we call something referred to as element level coordinate system. So even if you use packages, you will have something like global coordinate system, element level coordinate system, or element coordinate system. You will also have nodal coordinate system. So we will talk about nodal coordinate system later. For the timing, the nodal and the element coordinate systems are actually same, but this is for the entire element. So we are having origin. So when you, that means for in a package, if you are using a particular element and you need to specify something with respect to element coordinate system, or it takes some input with respect to element coordinate system, then you have to understand how that package is actually assigning element level coordinate axes. So either first node origin and then first to second node your x-axis, so and then perpendicular to that in the same plane y-axis, and then perpendicular to the xy plane z-axis, and so on. Or the element coordinate system is parallel to the global coordinate system. So there are various options. So but what we call this as element level coordinate system. So at this stage I just want to highlight that. So then in terms of, I want to write now this integral, because the integration is only over this particular element. So I can do that integration with respect to element level coordinate system. So element level coordinate system goes from 0 to small l, and we had here EA into du by dx. This I had done, so I am taking as it is. Now only thing is the derivatives are we can write the derivative with respect to global coordinate x is equal to derivative with respect to local coordinate x. So I would put these derivatives with respect to global coordinate. So that is, this is dx and this is also dx, capital X. Okay, so that's the first term. Then we had the second term, which is integral 0 to L u into q small l. Now keep in mind that this is small l dx. So this is we had already done, but see what we had done when we derived the integral functional, because we were talking about the entire problem. So we had those boundary terms 0, but now the boundary terms will not be 0, because here this element is somewhere in between. So neither at the end two end nodes of the element displacements 0, nor the forces 0. So there are forces as well as there are displacement. So we include the potential of those forces also, as we concluded that this is actually like this is strain energy first term, this is the potential of distributed force. We will also include the potential of these concentrated forces acting at right end and at the left end. So if you look at this force Q2E, you will have a corresponding displacement at this point. So let me also say that when I talk of this element, you have in terms of the displacement at this point is, let us say, again it's element label, so the numbers I am using for the element, let us say this is U1 for this element, and now at this node the displacement is U2. I want to put arrow little above so that it shows the displacement. So this is U2. What I am saying here, that when you apply the load and when you consider these 2 points within the domain, that is this point and this point, so this point moves by a distance U1 along the length and this point moves by a distance U2 along the length. So these are the displacements at this point and this point. So there is a force here Q2E, so work done would be Q2E into this U2, but this work done is positive work, so its potential is going to decrease with respect to undeformed configuration, because the force is moving, or the displacement is in the direction of force. So work is positive, potential is negative with respect to undeformed configuration. So the potential of this force is like this one would be Q2E into U2. If you look at this particular node, the force is in this direction, whereas positive convention for the displacement we are taking in the same direction. See, the forces are, sign convention for the forces is governed by outward normal to the cross section, what we are talking about here. Whereas the displacements are taken positive along whatever coordinate directions you choose. So if they are along the coordinate direction, they are positive. If they are in the opposite direction, actually displacement is in opposite direction and it's negative. So here, because the force is in the negative direction, finally this force might turn out to be negative, so that you have its work done positive. But for a positive case, this is force along the negative direction, whereas the displacement is in the positive x direction, so the work done is negative, so its potential is going to be positive. So this is Q1E into U1. So now your integral functional, in addition to this strain energy, potential of distributed force, has also these two terms which are coming from the boundaries of the element, not of the domain but of the element. And this is your potential of these boundaries and forces acting at the boundary of the element, that is here and here. So it's like when if you raise a mass at a certain height, so you're doing the work against the direction of force, against gravity, but then its potential rises, its potential is increasing from its initial configuration. But if it is moving, if you move the mass in the direction of gravitational force, its potential is decreasing. So if you take the datum as the initial starting position, if you go like this, potential is actually becoming negative, and if you from this as a datum, if you're moving like this, its potential is positive. So that's the interpretation for this term, why this is minus, why this is plus. So these two together is the essentially potential of all the forces acting on the element. So this is the first thing, that the integral functional for this element would be like this. We can also use weak form, but for the timing we are using integral functional. So the next step is approximate solution. So now we look at the approximate solution. We are now going to assume within the element, not for the entire domain. So within the element means I can use the local coordinate system, that is capital X. But then, and also let me say that we want to, for the simplicity, we want to use polynomial as the approximate solution. So now if you look at the highest order derivative in the integral functional, because that approximate solution you are finally going to substitute here. So highest order derivative is first derivative. So we must have at least linear approximate solution for u. So u is equal to then a constant term, say a0, plus a linear term a1x. That's capital X, I'm using the coordinate I have said. Now you can of course go for higher order terms, you can a2x square, a3x cube and so on, but this is minimum required from the differentiability requirement, that is finally we are going to substitute it here, so it should be differentiable at least once. Then second requirement is, what is the primary variable in this case, in this problem? It's a second order differential equation. Primary variable is only u. So u should be degrees of freedom at in nodes. So since we are going to connect this element with the other element, so it has to have two boundary nodes at least, and in each boundary node we must have primary variables as degree of freedom. So finally we minimum configuration of this element we get actually is this, with two nodes, left node 1 let's say and right node 2, with each node having degree of freedom value of the variable at this node as u1, value of the variable at this node as u2. So overall if you look at the element, it has two elemental degrees of freedom. That degrees of freedom is the unknown variables here, u1 and u2. Now these are discrete values at specific location. As far as this u is concerned, this is a function of capital X, but these are just, this u1 is the value of u at this point and this u2 is the value of u at this particular point. So we have once these two in nodes, each node having 1 degree of freedom, so total elemental degrees of freedom are 2. That's the minimum required to make sure that the primary variables, when we assemble these elements, are continuous across the element. We need minimum configuration of the element as this. And so in the approximate solution, since there are two elemental degrees of freedom, we can have at the most only two unknown constants. Now with these degrees of freedom, if I want to have one more term a2x square, it's not possible, because we would have three unknown constants in the approximate solution, which you are going to express in terms of these unknowns. You can't do that. So see, one is that first we wrote a linear polynomial minimum required based on the differentiability requirement point of view. Then we look at the continuity of the primary variables across the elements, and then look at whether we need to have more terms or less number of terms. In this case, it turns out that whatever is required from the differentiability point of view, same also satisfies this requirement that primary variables minimum are degrees of freedom at the in nodes. So then this polynomial is good enough. When we look at the fourth order differential equation, Euler-Bernoulli beam bending, we will see that from the differentiability point of view, you need only a quadratic polynomial, 3 terms. But then the inter-element compatibility, that is continuity of primary variables across the elements, requires that minimum you have to choose a cubic polynomial with 4 terms in it. So that would be an example where you would see that the final form of the polynomial is governed by the inter-element compatibility. So yeah, so let's see, if you were using strong form, so obviously here it would have been minimum quadratic. So since we are using a weak form, essentially your integral functional is nothing but is coming from weak form, and that is why the differentiability requirement within the element has reduced. So we only now have need to assume an approximate solution which is differentiable only once. So the next step is we need to express this a0 and a1 in terms of this u1 and u2. So finally we will have approximate solution which is in terms of coordinate capital X and u1 and u2. Then the coefficients of those u1 and u2 are referred to as shape functions. We will put all of that in the integral functional, and then we require for the equilibrium of the element that the first variation of this integral functional equal to 0 gives you element level governed equation. So I will continue the next class. I conclude today because I think there might be another class here. The students are already banging on the door. Okay. So if you have any doubts, you can ask outside. Probably there is a class here. Please ask the doubts outside. Okay. Probably there is a class here, I think.